We're living in a truly wild time for AI. The power of these new large language models is just staggering, and it feels like it's getting more powerful by the day.
I mean, we're now talking about million token context windows. To put that into perspective, that's like feeding an entire book series. Think Lord of the Rings, the whole thing, into an AI in one shot, and then just asking it questions. The promise here, right? It's huge. It's an AI with a basically perfect encyclopedic memory of anything you can throw at it.
But here's the catch, and it's a big one. It leads to this really fascinating and kind of frustrating paradox. You can give a model a whole mountain of text, but what happens when you ask it to find one single, tiny, crucial detail? The classic needle in the haystack. Does that massive memory actually work? Well, the answer is a whole lot messier than you might think.
And that brings us to what researchers are calling the long context problem. It is literally the needle in a haystack scenario, but for AI. And as we're about to see, the bigger that haystack gets, the more lost these incredibly powerful models become.
This chart just lays the problem out perfectly. So researchers set up a simple test. Find a single line of buggy code. When they gave the model a short snippet, maybe 20 lines, its accuracy was great, no problem. But then, when they hid that exact same bug inside 10,000 lines of code, look at that. Performance absolutely nosedives. And here's the thing you've got to remember. The needle, the bug, it didn't change at all. Only the haystack, the amount of code around it, got bigger. The model had all the information it needed right there, but it just couldn't pick out the one important piece when it was surrounded by too much other stuff. It gets lost in the noise.
Okay, so your first thought might be, well, why don't we just give the AI more processing power to think about it, right? In the AI world, we do this by getting the model to generate a chain of thought to work through the problem. Makes perfect sense.
But this is where things get really interesting. Take a look at that second bar. Giving the model more thinking time, it helps a little bit, but the improvement is tiny. It clearly doesn't solve the real problem. Just thinking more isn't the answer. But then look at that third bar. Whoa, a completely new method seems to have totally cracked it. To understand how, we have to meet the villain of this story.
So, the bad guy. The reason these super powerful models are failing is a phenomenon that the researchers have a great name for: score dilution. It's this invisible force that's messing with the model's memory, and it's the thing we have to beat.
So what in the world is score dilution? Well, basically, it's when the model's attention, the very system that's supposed to find the important stuff, just gets completely overwhelmed. When there's too much text to look at, its focus gets spread so thin that the one critical fact you're looking for just fades into the background. Think of it this way. Imagine you are in a massive, roaring sports stadium, and you're trying to hear one person, somewhere in that crowd, whispering your name. The whisper is the important fact, the needle. The roar of the crowd is the rest of the text, the haystack. Now, the whisper is there. You could hear it, but it gets completely drowned out by everything else. That right there is score dilution. So, what's happening under the hood is that the model gives a little relevance score to every single word in the text. But when you have millions of other words all acting as distractors, the score for the one correct word gets watered down and down and down until it's practically invisible. The signal just gets lost. So, if thinking harder with more brute force compute doesn't work, what's the fix? Well, this paper suggests a totally different approach. It's not about thinking harder, it's all about thinking smarter. And this slide just nails the difference. On one side, you've got the old way. Just make the model generate more text using the same old static programming. That's like telling the person in the stadium to just listen harder to the roar. Good luck with that. On the other side, you've got this new method called Query-Only Test Time Training, or qTTT. This is like giving our listener a pair of magic noise-canceling headphones that are specifically tuned to the exact frequency of that one whisper they're looking for. It's a game changer.
Okay, this qTTT thing sounds amazing, but how does it actually work? Let's peel back the layers here. It's actually surprisingly clever.
It's basically a three-step dance. First, the model does one super fast read of the whole document, just to get a general idea of what's where. Then, and this is the magic part, it does a few lightning-fast training updates. But it's not retraining the whole gigantic model, no way. It's only tweaking the tiny parts of its brain that are related to the specific question you just asked. And finally, using that newly sharpened focus, it spits out the answer.
So, if we go back to our stadium, this is like the model quickly learning the exact pitch and tone of the whisper it needs to hear.
It's not just listening harder to everything, it's actively tuning itself to amplify the needle and completely filter out the noise from the haystack. It's a direct attack on score dilution.
All right, so that's the theory. It sounds great on paper, but does it actually work in the real world? Well, the researchers ran qTT through a whole series of tough benchmarks, and the results? They're pretty incredible. Just take a look at this. This is a major benchmark for long context models. The first bar is just the standard model trying its best. The second bar is that same model but with extra thinking time. And that third bar, that's the model using qTT. I mean, the difference is just night and day. It's not even a competition. And this isn't a fluke. The gains are massive across all kinds of different tasks. Compared to just thinking harder, it gets an 8-point jump on finding bugs in code and a huge 16-point boost in answering questions from a pile of different documents. It just works.
And if you need one single number to walk away with, let it be this one. On another really tough benchmark, qTT delivered an average performance boost of over 14%. In the world of AI research, that is a gigantic leap.
So what does all this really mean for the future? This isn't just one cool new trick. This points to a much smarter way of using our computer power. I think the researchers themselves say it best, right here. It is just a flat-out better use of our limited computing resources to spend a little bit of time adapting the model to a specific problem, rather than just telling the same old model to spin its wheels for longer. And that's really the big takeaway. The future isn't just about building bigger and bigger models. It's about building smarter, more dynamic models. Models that can adapt and specialize themselves on the fly for the exact job you need them to do, right when you need it. It's a move away from brute force and towards real intelligence and efficiency.
And that leaves us with a really exciting, kind of mind-bending question. This new technique helps us solve the needle in a haystack problem. But if we can truly make our AI models adaptive, fine-tuning them in real time as we're using them, what other problems, the ones we think are impossible today, will suddenly become solvable tomorrow?